Hello again everyone, welcome back to ptet.chemistry channel. So in this continuation of these combined science, basically it involves very simple chemistry as well as biology and physics combined into one subject. This is a curriculum available for any 14 to 16 years old GCSE, IGCSE or O Level chemistry curriculum or combined science chemistry curriculum. Okay, so in this lecture tutorial we'll be looking at measurement of gaseous products. When you have reactions that produce gaseous product, how can you study the rate of reaction? Just to remind you, rate is to do with how fast the reaction is going, so it's how fast the reaction is. Of course, mathematically speaking, we will be looking at the change in the amount. So rate is just the change in amount over change in time. So amount meaning to say could be the mass of the reactants that are being used up, could also be the volume of your products that you are forming, and this is to do with the change in time. So this was the bit in the syllabus where earlier on the learning objective at the very beginning of this topic, we talk about candidates should be able to interpret data, including graph from rate of reaction experiments, as well as thinking about practical methods to investigate rate of reaction, especially when you form a gas there. So we're going to be talking about gas collection, but there will be the second bit that we'll talk about. I've decided to talk about the loss in mass first. So when you have reactants that can react, such as these dilute HCl and marble chip. So marble chip is actually calcium carbonate. So calcium carbonate consisting of the group 2 calcium ions. So it lost 2 electrons to achieve a fully filled outer shell, which is calcium 2 plus there. You're going to get carbonate CO3 2 minus. These are your year 9 chemical formula. When you look at the valency is just based on the charges. The charges is 2 plus there, so the valency, which is the number, is just 2 following the charges. When you do the crisscrossing, the cross multiply, then it becomes 2 and 2. This is basically how many, but then they are not the simplest ratio. So you can divide 2 on both sides in order to get the simplest whole number ratio. So you want the whole number ratio. As you can imagine, this is going to be 1 of that calcium 2 plus combining with 1 of that CO3 2 minus. That's why we get CaCO3 for the formula of calcium carbonate. So the name is calcium carbonate. So carbonate ion is that CO3 2 minus ion there. Okay, so we're going to be investigating this reaction. If you think about your year 9, this is year 9 chemical equations. So you have learned the general equation when you have a metal carbonate. So metal carbonate plus acid, you are going to get a metal salt. Because you are also reacting a carbonate, so the important thing there is the carbonate plus the acid. You're not going to produce hydrogen, you're going to produce carbon dioxide gas. And you also get a third product, which is just water. In terms of chemical equation, we can also write calcium carbonate plus HCl, hydrochloric acid. So you're going to get calcium chloride, CaCl2, calcium chloride, Ca2 plus, Cl minus, 2 and 1 for the valency. We are doing the exact same thing as what we did in year 9. So 1 of calcium 2 plus combining with 2 of Cl minus, you're going to get CaCl2. Carbon dioxide, your year 9 covalent bonding topic, CO2. Your year 9 covalent bonding topic, water. We got to balance our equation. 2 chlorine, this is your year 9 under chemical equation. So 2 chlorine atom, 2 times 1, 2 chlorine atom, we cannot change the identity there. We're going to get CO2, 1 oxygen goes here, so 2 plus 1 give you 3 oxygen, so that is balanced, 1 carbon, 2 hydrogen, 2 times 1, 2 times 1 there. Anyway, so we know that calcium carbonate is your marble chip, so that one is your solid. S there in the bracket refer to solid. Acid is going to be aqueous. Calcium chloride is aqueous solution. Carbon dioxide is a gas that even as we speak, we are breathing out because we are doing respiration. We are respiring, and it is just liquid water left behind. What is important is this CO2 that's produced as a gas. So what will you see? We will see bubbles because we observe bubbles because gases are being produced. We do not observe CO2 because CO2 is colorless. Be very careful about what do you see. You cannot see CO2. It's in front of you, but when it's produced in in the solution, you're going to see bubbles coming out from the solution. There's going to be the CO2. But the fact that you are losing CO2 as a gas, therefore you are losing masses because this thing is being disposed of, is leaving as a gas. So your mass is going to decrease. This is a loss in mass. Loss in mass is going to increase until eventually it stops. So here, the loss in mass is increasing. So you can say the loss in mass is increasing. More and more mass are being lost because CO2 gas escape. But here, where does it stop? So here we can see towards the end, it stops. No more change in mass. No more change in mass. No more change or no more loss in mass. No more mass loss. Why? Why is that? Well, the fact that if you don't get any more carbon dioxide being produced, that means no more reaction is taking place. So that means the reaction is complete, because when the reaction is complete, you get no more change in mass, but whatever you have lost is already just that value, because that's what you have lost up until that point when the reaction stopped. No more reactions, reaction stop. Okay, so we can use this graph. This graph is showing us the change in mass, the loss in mass over the time. So from this graph, the gradient of the graph, the change in the loss in mass over the change in time is going to give us the rate of reaction. So that's what it's saying there. Okay, so we can monitor change in mass per unit time when the gas is allowed to escape. And the second one we'll be talking about is collecting the volume of gas produced per unit time. So we can also collect the volume of gas per unit time. This is about gas collection. So gas collection means you have to collect the gas. You have to read the volume of the gas inside this thing called a gas syringe. A gas syringe has got these graduated lines. The graduated lines basically tell you readings, and if you can read off the volume as the piston get pushed out, because the gas particle keep on pushing on the walls and therefore occupy the space there. So this is the exact same reaction, HCl and marble chip. So HCl and calcium carbonate giving you carbon dioxide. Instead of allowing the carbon dioxide to escape as was in the first example here, we are going to allow the carbon dioxide to be collected inside the gas syringe. And in doing so, we can read the volume of carbon dioxide produced at a given time. So having said that, you need to change the time. So this is your x-axis. This is going to be your independent variable. Independent variable is what you change. You change the time and then you measure the volume of carbon dioxide. So what you measure is on the y-axis, and then we talk about dependent variable because why are you so dependent? Why are you so dependent? So the y-axis is your dependent variable. Very, very important there, because it is what you measure, is what you record. As you change the x-axis, there's the independent variable. What you change, what you vary. Okay, so yeah, I mean, it's exactly the same reaction. It's just two ways of monitoring or studying the rate of reaction. One was using the change in the mass, because the gas is escaping, so the mass of these reactants inside the conical flask at the beginning will keep on decreasing, and you can plot the loss in mass or change in mass against time. Or you can plot the volume of gas collected against time by using a gas syringe to collect the volume of gas there. Okay, so forget about these other reactions. They will be removed by the time you actually that you receive these notes. These are actually more advanced stuff. I was just using the notes for that from that very good resources, so don't worry about that at all. Okay, I'll leave it here for this lecture tutorial, and we'll continue more with two particular examples in the next lecture tutorials on these methods of studying the rate of reaction. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected.